How do you measure the precise physical properties of something so incredibly small that you can never actually see it? By the early 1900s, the electron's negative charge was accepted fact. But because the particles themselves were so small, no one had been able to measure the actual quantity of electricity a single electron held. That changed with the work of physicist Robert Mulliken and his graduate student, Harvey Fletcher. Instead of trying to isolate a single invisible electron, they relied on a bit of radical logic. They decided to measure the electron's effects on macroscopic objects, things they could actually observe and control in a laboratory. This was the era of mechanical physics. Breakthroughs didn't happen on computers. They happened in rooms filled with brass dials, glass tubing, and machinery. Calculating the charge of subatomic building blocks didn't require a particle accelerator. It required a delicate balance of gravity, electricity, and a brilliantly engineered mechanical setup. The first requirement was creating the test subjects. They used an atomizer, like those on antique perfume bottles, to spray a fine mist of droplets. But why use oil for these droplets, rather than a basic liquid like water? It came down to the environment inside the chamber. To actually see these tiny drops, the scientists had to blast them with an intense light source. That light generated heat. If they used water, the droplets would evaporate under the heat, constantly losing mass and ruining the calculations. The engineering solution was highly specific. They utilized a specialized oil designed for vacuum apparatuses because it possesses an incredibly low vapor pressure. By selecting this exact liquid, the droplets remained perfectly intact under the harsh lights. Their microscopic test subjects were successfully isolated from any thermal interference. This diagram shows the main vacuum chamber where the experiment took place. Notice the two distinct metal plates, a positive one at the top and a negative one at the bottom. The atomizer sprays the oil into the top section. Gravity pulls a few of those droplets down through a single, tiny hole in the top plate, allowing them to fall into the main viewing area. As the droplets fall, ionizing radiation is fired into the chamber. This knocks loose electrons from the air, which immediately cling to the falling oil drops, giving them a negative charge. Mulliken watched this entire process through a specialized viewing microscope. Lit by the intense beam of light, the tiny drops appeared like bright falling stars. Then he flipped a switch. Thousands of volts charge the bottom metal plate negatively. This initiates a physical tug-of-war. Gravity naturally pulls the mass of the drop downwards. But because the drop now carries a negative charge, the newly electrified negative bottom plate strongly repels it upwards. By meticulously tuning the voltage, Mulliken could balance these two competing forces. He adjusted the dial until the upward electrical push completely canceled out the downward pull of gravity, freezing the droplet perfectly still in midair. Once the drop was suspended, he had his answer. He already knew the force of gravity pulling down on the drop's mass. By equating that known downward force with the upward electrical voltage holding it in place, he could finally calculate the invisible electric charge. Mulliken repeated this balancing act for thousands of individual droplets, logging the total electric charge resting on every single one. Look at this massive dataset. The measured charges strictly clustered on distinct horizontal lines, leaving empty space between. Every calculation was an exact multiple of one foundational number, 1.6 times 10 to the negative 19th coulombs. Some drops carried twice or 3 times that charge. This data perfectly illustrates the concept of quantization. Electrical charge operates like a staircase, not a smooth ramp. You can have 1 step, 2 steps, or 3 steps of charge, but you can never exist at step 1.5. This finding was a breakthrough. That indivisible base unit they discovered is represented by the letter E, the fundamental elementary charge of nature. Mulliken's brilliantly engineered machine proved that the universe doesn't deal out electricity in a random, continuous spectrum. It distributes it in strictly measured, quantized packages. If you enjoyed this breakdown, make sure to subscribe to The Explainer. We translate complex physics concepts into